All right, we are going to continue with the round 2 training program that we stopped at. And now we're going to go on to problem number 23. Problem number 23 states the following: in the equation YE times ME equals TTT, each of the letters represents a different digit from the set 0, 1, 2, 3 up to 9. Determine E plus M plus T plus Y. So the problem is to find these digits. These are digits. So you got a 2-digit number here, multiplied by a 3-digit number equals another 2-digit number equals a 3-digit number. A quick examination of this will tell you that all these numbers are the same. So it could be 111, 222, 333, or whatever, going all the way up to 999. So in fact, this is 111 times T. So that we can see it's a multiple of 111. On this side, you've got the same endings, EE. The units digits are the same. All right. So now how do you find what these letters represent? Well, the clue will lie here, because we know this is T multiplied by 111, but you want 2-digit numbers. So 111 itself factorizes as 3 times 37. 3 goes exactly into it. So this quantity here is 3 times T times 37. So evidently 37 is going to be one of these numbers, because this is 3 times T times 37, and 37 is a 2-digit number. So it's going to be one of these numbers. And that immediately tells you that the units digit of 37, that's what we are interested in because it's repeated, it has to be 7. The units digit of 37 is 7. Therefore, the units digit of the other number is also 7, because they both have the same units digit. But then, when you multiply these 2 units digits, 7 times 7, that ends in a 9. So T will have to be 9. So this is 999. And once you got this is 999, then it means it's 9 times 111. And you take 3 out from 111 and you get 9 3s are 27 times 37. So the numbers that we're looking for is 27 times 37. All right, so you got 2, 7, 3, 7. So the numbers are 2, 7, 3, and 9. And you can add all of them up. I think you get 21. Yeah, 3, 7, 9, and 2. So we actually did that mentally. It wasn't a very difficult problem. Clue is 111 is 3 times 37. So 37 is a 2-digit number. It's a factor of the right-hand side. Therefore, it must be one of the numbers in the left-hand side. Okay, we'll just go on because that wasn't a very difficult problem, although it's one of the later problems. Now here we have a geometry problem, number 24. Right-angled isosceles triangle ABC has A equal to 90 degrees. Let's just stop there. So this is a right-angled triangle. I can see it's ABC, A, ABC, ABC. And it's isosceles, that's important. So it means that these sides are equal. AB and AC are equal. So these angles are equal and they add up to 90. So immediately you know that these angles are 45 degrees because it's isosceles. So angle C is 45 degrees and this entire angle there is also 45 degrees. All right, so that's the information. The information right in the beginning allows us to make these conclusions. Now, E is the midpoint of AC. So you got E is right in the middle here. These two lengths are the same. F is a point on BC such that FE is perpendicular to EB. So you join B and E and you drop a perpendicular. And where it meets the hypotenuse, that point is F. It's also given that AB equals AC equals 40 times root 3. So AB, AC. So they are both equal, 40 times root 3. Bearing that in mind, what is the area of triangle CEF? The small triangle sitting here in the corner. So what is the area? We just have to remember what the given facts are. These two are equal. This is the right angle. And these angles are 45 degrees. You also know the length of AB and AC. They are equal lengths. It's isosceles. All right, now let me just go back here. Go back to this previous picture before we go into the solution. So you want to calculate the area of this triangle. There are two basic formulae to find the area of a triangle. One is the half base times height, and the other is the formula which says the area is half AB sine C. So it may very well happen that we need to calculate that one, half AB sine C. All right, so we need the sides of these. All right, these two are equal, and we know this is equal to the whole thing. And we know that the whole thing is 40 root 3. So we should know that this is 20 root 3, and this is 20 root 3. So we're getting somewhere. We can find the side here. We can find the side. Now, I need to find an angle and the other side. All right, so if we know this side here, we know this side, and we know this whole side. So you know this side and this side. So as far as this triangle is concerned, you know two sides of the triangle. So it means that you know you can actually calculate the angles, right? Because if you look at that angle, the tan of that angle is a half, because this thing here is half of the whole thing, and this whole thing is equal to this. So the tan of this angle that I'm pointing to is a half. You know that what that is, but we don't know what the actual angle is, and we're not allowed to use a calculator. So you only know that the tan of this angle is a half. So you can even say, you know, the trig ratio of this angle, because this is the complementary angle to this. Now you'll notice that these two also are complementary here, this angle here and this angle here, because this is 90 degrees. So this angle here is the same as that angle, because the angle that I'm pointing to is 90. Well, this angle here, this angle is 90 minus that, and this angle is also 90 minus that. So these two angles are the same. So let's give a name to this angle here. If we know, give a name to this angle, we know all the trig ratios of that angle, because you've got, this is, the tan is 1/2. If you know one ratio, you know them all. You can calculate the hypotenuse and you can work out the others. But now you also know the trig ratios of all of this angle here, CEF. You know all the trig ratios of that. You got this side here. So it looks very much like as if we need to work out this side here. And then you can use the formula half AB sine C. So I need to calculate this angle or this side. I know this. Pythagoras will tell me what that is, BE. right? And the only thing you have to do is to see this angle here is 45 also, and we know this whole angle here. If we call this angle here theta, this angle here is also theta. And we said earlier on, it's 90 minus this angle is this. 90 minus this is also that. So we call this angle theta. This is theta, and we know this, and we know that there is 45. So you got 45, and this is theta. So we know this angle here is 45 plus theta. 45 plus theta. It's the exterior angle of the small triangle. All right, so you know this angle and you know this side. Okay, so you should be able to calculate this one because you know this angle here. So you know this and you know that, and therefore you should be able, yeah, you know this and you know that angle, you know the trig ratios of this angle, you should be able to calculate this side. Once you calculate this side, then you know this side and you can use that formula. See, there's a lot of calculations involved here. So let's just go through this thing quickly. You've got the general principle. I'm naming this angle here, and you can see it's going to be equal to this because this angle is 90 minus this angle that I'm pointing to, but 90 minus this is also that. So we're giving names now to these. We're going to call this A and B, and this is going to be 2A because tan of theta is, well, I mean, this whole thing is 2A, so therefore that will have to be 2A. So tan of theta is a half A over 2A. All right, now we give names to this A and B. So the area of the triangle we're looking for is half AB sine theta. We know A, we can substitute for A. We don't know B and we don't know theta, but we know the trig ratios of theta. All right, now let's have a look at this now. You got A and you got 2A here. So you can, by Pythagoras, this will be A squared plus 4A squared is 5A squared, so you can calculate this. 5 square root of 5A squared, which can be written as A times square root of 5. So you got this as A times square root of 5. And you know that this angle here is 45 plus theta. So you got B and you got here, this is A root 5. So we can use this side and this side to get the ratios of this angle here. So we are actually looking at the angle EBF. EBF. This angle here, this is 45 plus theta. These two angles add up to 90 degrees. If this is 45 plus theta, that has to be 45 minus theta. Why do I do that? Because I know the trig ratio of this angle. It's 45 minus theta. Okay, there is, at this stage, we can calculate theta by, well, tan theta is equal to a half. So we should be able to, we know what the tan of theta is. But now you got a 45 minus theta and you got 45 plus theta. And you need to know the trig ratios of those angles. Specifically, I need to find out what B is. So we take the ratio B and you put it over that, which is A root 5. From Pythagoras, you get square root of 4A squared plus A squared, which is square root of 5A squared. So this is A times square root of 5. So you know B over A times square root of 5, this is what I've got here, is equal to what ratio of that angle there? B over that is, from this viewpoint, B is opposite over adjacent. So tan of this angle is b over a root 5. So I've got another equation now. Tan, there it is, b over a root 5 is equal to tan of 45 minus theta. Now there is a formula. These trigs, this is formula. The tan of a difference is actually equal to, there's a very nice symmetrical formula. Tan of a difference is equal to tan A minus tan B all over 1 plus tan A times tan B. Please learn this formula. It's a very important formula. It comes up in quite a few Olympiads. The tan of a difference. In school, you learn much about the sine and the cosine of the difference. But in Olympiad problems, this one comes up often. So tan of 45, tan of A minus B, we know what that is. All right, now we're going to continue calculating tan of 45 minus theta. You can see I'm going to the next line. So this is tan 45 minus tan theta, tan 45 minus tan theta, all over 1 plus tan 45 times tan theta. Okay, now tan 45 is 1. It's a very beautiful, very simple value for tan 45. It's 1. And tan theta is a half. So I can substitute straight away. 1 minus half over 1 plus half, because this is tan 45 is 1. So remember that as well. Tan of 45 is 1. And this can, you just use the ordinary fractions. This is a half over 3 over 2. And those halves cancel and you land with 1 over 3. So b over a root 5 is 1 over 3. So now that immediately tells you what b is. You can calculate b, cross multiply. 3 times b is equal to a root 5. So b is equal to a root 5 divided by 3. All right, so you got b, and we know what a is. A was given 40 root 3 or something. I'll come back to that. So you know this, and you know that. Right? This is a. And this is also in terms of a, it's a root 5 over 3. So the area of this triangle is half that times the sine of theta. Sine of theta. Now, sine of theta, we know what sine of theta is because theta is sitting up here. So sine of theta is opposite, which is a, over hypotenuse, which is a root 5. So sine of theta we can calculate. So there we are. We've got we need to calculate the area of CEF. Area of CEF is half CE times CF times the sine of the angle between them. So let's see. Can we simplify that? It's half AB sine theta. So we write that on half AB. And sine theta is 1 over root 5. So that is going to be A over A root 5, which is 1 over root 5. So you can substitute for that. And then you can substitute for B, which is A root 5 over 3. And eventually you get just A. Yeah. So you got that the area is 3 times 2 is 6. So the denominator goes down there. And the numerator is A squared. And A is half this length. So if you know that length, which is 40 times square root of 3, you know what A is. It will be 20 times square root of 3. Okay. And when you simplify this, you get a beautiful answer. You got 200. All the square root of 3, square root of 5, all those things all disappear. And this is where you are. Okay. All right, that takes me to the last problem for tonight. Okay. Now this is quite a strange problem. What is the smallest integer larger than √3 plus √2 over 6? The calculator will give you the answer very, very quickly. But you're not allowed to use calculators. And you're going to raise some number to the power of 6. And that number is not even a nice, decent number. It's got a √3 and a √2 in it. It's useful to know what the root of 3 is approximately. You should remember that the square root of 3 is 1,7 approximately. It's 1,732. Actually, to 3 decimal places. So, the square root of 3 is approximately. You should have an approximate sign here, which I haven't got. And that's going to be 1,7 approximately. And read that as approximately equal to. Likewise, the square root of 2 also, it's nice to know this value. And that's about 1,4. Okay. But even if you add these two up and raise it to the power of 6, you're not going to get anywhere near the answer. You have to think of some other way. Now, whenever you got square roots added like this, two numbers, and you got a square root there somewhere, one gut reaction which you should apply is you give a name to the same thing with a negative sign in between. So you give a name to √3 minus square root of 2. Call it A. So this is what we are doing here. All right, so once we give a name, okay, we give a name to A itself, the √3 plus √2, we give a name to it. We're calling it A. And then the problem is to find A to the power of 6. Don't lose sight of the goal. Right? The goal was to find that quantity, Cartesian's number. The goal is to find the 6th power of this quantity here, which is A. All right. Now you can have some very nice algebra here, and I'm going to show you what you can do. If you call this A, take the same thing with a minus sign in between and multiply these two. √3 plus 2 times √3 minus 2. Now, difference of 2 squares tells me that this is 3 minus 2 and that's equal to 1. It simplifies very, very nicely, this product. Okay, so, which means that this quantity here, √3 minus √2, is actually equal to 1 over A, because I'm giving a name A to this. So √3 minus √2 is 1 over A. So we got this is A and this is 1 over A, and I'm going to add these two, A plus 1 over A, these two here, and you see the √2's cancel off and you're left with √3 plus √3, which is 2 √3. So A plus 1 over A is 2 √3. And what is A? A is this quantity here. I need to calculate the 6th power of A. All right. Now, this is a very famous identity here, namely that if you've got A plus 1 over A or X plus 1 over X or T plus 1 over T, whenever you got a thing like that, it's a very useful thing to do is to square both sides. So when you square this side here, you're going to get this squared, A squared plus 1 over A whole squared, which is A squared plus 1 over A squared. And there's a middle term as well, which is 2 times a times 1 over a. The a's cancel, and you got 2. So a squared plus 1 over a squared is this whole thing squared minus 2. So you have to take out the middle term, and you have that these two are equal. But we know what this is, because a plus 1 over a is 2 root 3. So this is 2 root 3 all squared. And that gives you 4 times 3, which is 12, minus 2, and that's 10. No complicated calculations. 12 minus 2 is 10. Okay, now we need to get to the a to the power of 6. And a cute way of doing this is to take this and square it. You can go up to a to the 4th, plus 1 over a to the 4th. And you presumably have to multiply these guys to get a to the 6th. So we worked out what a squared plus 1 over a squared using the fact that a plus 1 over a all squared simplifies to that. Okay, now to get to a to the 4th plus 1 over a to the 4th, all you have to do is to square this thing here. When you square this, you'll have a to the 4th plus 1 over a to the 4th. Right? But there's a middle term, which is 2. So you're squaring it. 10 squared is 100, right? And you have to take the 2, the middle term, take it out, and you have 98. So a to the 4th plus 1 over a to the 4th is 98. Now what is a to the 6th plus 1 over a to the 6th? Well, it looks as if you have to multiply these two things to get this, but it's not quite right. Okay, let's see. On the one side, you've got 10, and on the other side, you got, no. Yeah, you got 98. This is 98, and I'm multiplying these two. So 98 times 10 is 980, and that is equal to the product of these two. Okay. You could have done it like that, or you could have factorized, which I have done, a to the 6th plus 1 over a to the 6th, and regard it as a cube, sum of cubes. When you regard it as a sum of cubes, then the first factor is a squared plus 1 over a squared. The second factor, by now you should know that the first term is the square of this. The middle term is a product of the two, but with a minus sign in front of it. If there's a plus here, this becomes a minus. And these two, if you square it, you get 1 over a to the power of 4. So now we know what these quantities are, because this part here is 10. This part here is 10. And this part here is a to the 4th plus 1 over a to the 4th, we worked out to be 98. Subtract 1, you get 97. So this is 10 times 97, which is 720. I should have cleaned this thing out. Okay. So you got this plus this is 970. And we really need to recalculate only a to the power of 6, an approximate value for that. Now, if you analyze what 1 over a to the power of 6 is, you get quite a interesting story. Because 1 over a to the power of 6 is root 3 minus root 2. There's 1 over a. 1 over a is that. So 1 over a to the power of 6 is this raised to the power of 6. Right. Now, we don't have to work out this complicated thing, but we can say that this is 1,732 actually, 1,732, and this is 1,414, and you can subtract those two things. The reason is I just want to see what is this approximately equal to. Then you get 0,3 raised to the power of 6, 0.3 raised to the power of 6, and this is the answer that you get. So what are we saying? We are saying that 1 over a to the power of 6 is very, very small, because what we've got here is a to the 6th plus 1 over a to the 6th. We got it's approximately equal to 9. It's exactly equal to 970. So this quantity here is very small. Look at it, very small as compared to this whole thing. So we can actually say that this is equal to 970 minus that. And this quantity is very small, so the closest integer, which is larger than this, is 970. You're subtracting a tiny little quantity from 970. And the closest integer larger than 970, larger than this, is 970. Okay, so that's a complicated, well, the idea is when you got this kind of object, see all over here, then you can calculate all of these if you know this. You just have to know this. And you can calculate every one of these, like what I've done now. So this is a squared plus 2, the middle term, plus 1 over a squared. All right. So that's the problem number 25, the last problem on 2018. And next time we meet, we will be discussing new problems from other years. Okay, we finished 2018, so probably we'll go into 20. This is 2019, 2018. I don't know what happened to 2019. Okay. Thank you very much. We will continue these little discourses in a short sometime in the near future. Thank you very much and enjoy the rest of the day.